Okay, great. So I'll be discussing on a research paper that's named GLoVE. So it looks something like this. To be honest, I'm not really a very big fan of reading the research papers, but it seems practically impossible to understand all the technological advancements that's happening in the field of AI without going through the research papers. So I spent around one day trying to read this paper, try to understand this mathematics, which kind of gave me a panic attack, and I tried to summarize the high-level concepts of it, mathematics behind it, why do we use it, and where do we apply it, and what is an advantages with this kind of embeddings. So I had prepared a small presentation over here, which is basically 10 slides. It's not much, so stay with me. So what is GLoVE? It is a global vector of forward regularization. Now it sounds fancy, but doesn't say much. So we can just see what it is doing and what is the logic behind it. And we're going to try comparing it with few other predecessors, and we're going to see how it is in the implementation part of it. So how it is actually helping us in understanding or enhancing the embedding models that we already have. So let's see what is GLoVE. It derives a semantic relationship between word using word-to-word co-occurrence matrix. Doesn't say much either. What does it even word-to-word co-occurrence matrix means? Let's say you have a whole corpus of data. So for the sake of simplicity, I took a smaller amount of data. Let's say there are two sentences. I love something something. I love data science. So what I'm trying to do here is I'm trying to create a matrix of all the words, of all the unique words in the data set, which is my case. It's like really a small amount of data set because it's easy to visualize. So I try to map the correlation between all these words. I have kept the window size to be 1. So for example, if I is present next to love, then I'm going to put 1 marks there. So since it is present 2 times, I'm going to put 2 marks there. And you're going to see the same actually over here. And I'm trying to find the correlation, the possibility of occurrence next to some word, and I'm going to mark it. So at the end of the time, I get all the unique words listed on the rows and columns, and it gives me the possibilities of co-occurrences. So it's in the plain numbers. It would be nice if we have it in the probabilities. So we use something called P of ij, which is probability of some word in the ith row to the probability of some row in the jth column. So it can also be represented by P of where I is present with respect to P of where J is present. So it is like just different representation forms of it. And let's take an example. So the probability of I being next to love is 2 by 2. And how is it? If you see love, it's present 2 times close to the I. And the total number of I in the total number of I that's present in the whole corpus of data is 2. So the probability is 1, which means it's 100% probability that I will occur with the love given this data. It's just based on this data. So let's see with some solid examples. So this is an example that I have found in the research paper. So the probability of I's being solid is 0.5, which is like 50% probability. The probability of I's in relation to gas is very small. So the probability of ice in respect to water is somewhat neutral, like 50%. The probability of ice with respect to fashion, which doesn't have any sense at all, which is basically 0. So the same goes for steam. So using this, we can come to a ratio matrix, so which looks something like this. And what we are doing here, we are taking individual words and creating a vector, which is basically a fake embedding, or we are initializing with some dummy weights. And we have a loss function that kind of compares this dummy representations to the actual target values. And it kind of trains the model to create embedding that better suits the word. That's what we are trying to do here. And technically, mathematically, imagine there is a formula that you can use to achieve that. So plug in this formula, give in all the inputs, and it throws out the embeddings. You try it over 100 or 1,000 or 10,000 at most, you get a better embeddings. So I don't want to show the whole derivation here, but just imagine, just believe me, there is a way that we can solve this problem mathematically. And what are the advantages with the GLoVE? So GLoVE solves a few important things. So one big advantage is it solves a very frequent and very infrequent co-occurrences. And it also gets rid of the duplication, which is a very common problem with word-to-vec, which is skip, gram, and zero models. So the performance, you see, in comparison to the CBOW, the accuracy rate is sharply increasing with the more number of iterations. If you see it with SkipRAM, which is quite a flagship one, so the accuracy is also increasing steadily, but also the accuracy is quite higher with a very lower number of errors. So that's really an advantage when you're training a large model because it saves you a lot of resources, time. So GLoVE outperformed in all the compared to the previous flagship models. So yeah, enough talking. Let's code. So the most important part of creating an embedding model is to see how it is actually helping us in the real world. So what is a practical application of GLoVE? So let's come to the implementation part. I tried to create my own GLoVE models, my own embedding, but it was a failure. So I kind of downloaded a GLoVE embedding from the internet. So this is something like this. So I have assigned the GLoVE model. And what I'm trying to show here is the most similar words that's close to love. And if you see, it splits the probability. And I have shown the top 10 probabilities. So loves, passion, love, romantic, lovers, lover, you, me, affection, always. So these words are kind of closely related to the word love. That's what basically we are showing here. And we got another textbook example, so which is basically husband minus man plus women equal to wife. So if I give you this question, so you can just look into the words, understand the context of it, and give me an answer. It is wife. But what I want to achieve is to create a numerical representation of these words. So if we do this subtraction and addition, it also gives us the same output. So technically we are trying to create a numerical representation, which is basically embeddings that kind of behaves the same way as a natural language. So which is very important when it comes to NLP, all the ChatGPT models. So what you're trying to do is you're trying to find the most similar words, and I'm kind of adding the woman and husband, and I'm kind of reducing the man from it. And I'm trying to see the top 3 results, and it has thrown out perfect probabilities. Wife, mother, daughter, which are all closely related to the output that we are expecting. So it's just a proof that the embeddings are working as expected and they're good to proceed forward. So I took some examples, dummy examples, to prove my point again. So which has a unique vocabulary of 18 words. So what I'm trying to do here is to assign the embeddings. So in this case, there are like 300 embeddings for each single word. Try to put it in a data frame. That's what I have shown here. And I'm kind of fitting it in TSNA model. So TSNA model is basically for visualization purpose. So there are like 300 dimensions in our data. Obviously, it's really hard to wrap my mind or your mind around 300 dimensions. So it will be better if I can see it in X and Y planes. So I'm trying to reduce it to 2 dimensions and some other parameters to issue the random state and all. I'm trying to fit the model and visualize it. So if you see, all the pair guava banana are kind of assembled on one side of the graph. All the Apple, computer, mobile. So I do understand why Apple has been assigned close to computer because, yeah, it's for obvious reasons. And we have brother, husband, wife, and sister. All the cities on one side, the colors on one side. So the model kind of perfectly understands the relationship between the words. Not so perfectly, but better than nothing. So, and it kind of shows it in the graph how it would occur close to others. So if you plan to try out this code, I have given a link down for my GitHub repository, and I have also given a link for my for the paper. So if you're interested in looking into it further. Yep, so thank you for your time. See you another week with another paper. Take care. Bye.